Alrighty, so today we're going to be talking about recurrent neural networks, or RNNs for short. But before we go into that, let's just do our usual recap of last week's lesson. So last week's lesson was all about CNNs, or convolutional neural networks. And really at the heart of a CNN is the convolution, which is really just you take what is called a kernel. It could also be just called a filter. But at the end of the day, all it is just a matrix. And so you take that kernel and you slide it over the entire input, which is usually an image. And so you slide it over, and what you're doing is a pointwise multiplication and then summing up all those elements. So what you see here, the kernel is multiplying only the diagonal elements, both diagonal elements, by 1, and everything else it's completely ignoring by multiplying by 0. And then it just sums them all up. And so you slide that over, and because, like we talked about last time, those very, very corner pixels will never be at the center of the kernel, in the process of sliding this convolution over the image, you are actually reducing the size of the image, because the very outer border is not going to be like at the center of the kernel. It'll only be on the edges. So you end up with a smaller output than there is an input. And so the whole point of doing these convolutions is to learn in kernels. And just mathematically, we know of certain kernels that by definition do really cool things. So this one, which we learned about last week, this is called the Sobel kernel. And this is really, really good at edge detection. So the one that you see here, and as I mentioned last time, there are actually 4 Sobel kernels, but all of them are just simple 90-degree rotations of each other. And so could someone remind me, this specific matrix that I've shown here, which type of edge does it really highlight, or does it make very, very bright white? Would it be the top, bottom, left, or right? Does anybody remember? Yeah, so Isaac is putting in the chat top. Avi is also agreeing with that. Yeah, that's exactly right. And just for that intuition again, the reason that it does that is because we have positive weights on the top layer and negative weights on the bottom layer, so that when you're sliding over an image, and let's say that you have like an edge at the top, you would get a very, very positive value at the top. And you want to discourage there also being a bottom edge, which is why you have a negative edge there, so that when you sum it all up, you get an overall very positive value. And then, yeah, if you just took these numbers and just rotated them 90 degrees to the left, so that the 1, 2, 1 was on the left-hand side, the same exact thing would happen, where if you had an edge on the left side of the kernel, that would register as very positive and end up, because positive is white and black is negative, it would end up colored as positive in the final image, which is what you see here. So this final image on the right-hand side is actually a composition of all 4 Sobel kernels. They ran each one and then composited all the images together, and you get this really sharp defined edge detection. And the other part of a CNN was the pooling. So pooling is not as cool as convolutions, in my opinion, because it doesn't like actually learn some interesting or relevant information from the image. It's just a straight up method of dimensionality reduction, or in other words, reducing the size of the image. And so this specific one is called a max pool. This is also what you guys used in the notebook. It's just you take this 2x2 kernel, but really all you're doing is just in each 2x2 window, you're taking the max of that window. Like we talked about, the reason that it's 2x2 and not 3x3 is because of the stride length. We're not moving over by 1. So it's not like we go from this square to this square. We stride by 2. So we go from this square to this square, and then from this square all the way down to here, etc. So hopefully that was a good recap so far. And one thing you should note is that of CNNs, and everything we've talked about so far with regards to neural networks, it's always been a fixed input size. You cannot have like a variable input size. You could have like a really, really big input size and you decide to feed it in something smaller, but then you would have to pad the rest of the neurons with zeros or like pad them with some sort of values. The input size is always fixed. That's just one thing to keep in mind, because that's not true for RNNs, which is what we're going to be looking at. And another thing is, of course, we had to pre-process and resize the images before inputting them into the CNN, just to kind of drive home that point that it is a very specific size that needs to be inputted into the network. So the motivation for RNNs is different. So the whole benefit of CNNs is that they were really, really good at looking at spatially related data, which is why they're used all the time for images, because images obviously have a lot of locality, like there are local groups of pixels in space contain information just by being similar to each other like location. But RNNs, on the other hand, are really, really good for anything that comes in sequences. And there are all sorts of data that comes in sequences, as we're about to see. But another really, really big advantage of the way an RNN works is that it could actually have a variable infinite size input and output. So that's a big plus, but we'll see, there are drawbacks that come to this as well. And I'm going to check the chat real quick. It seems like, okay, never mind. So yeah, some forms of sequence data that we can look at. So machine translation is obviously a big one. When you go into Google Translate and you're typing in a variable input length sequence of words, and you're getting out a variable output length sequence of words in your target language. So that's a great example. DNA, obviously, I mean, a DNA sequence, it's in the name itself. The sequence of nucleotide bases is what defines what protein is going to be made and all that stuff. At the bottom left here, you see like stock that's showing like stock prices. That's a sequence over time. So that's time series data of how the price is changing over time. And on the right here, you see heartbeat data. So that's also a time series. So these are all examples of different types of sequential data that RNNs would be a really good fit for. So now let's get into a little bit of different types of RNNs and what they could be used for. So in this picture at the top here, you see one-to-one, one-to-many, many-to-one, and many-to-many. First of all, right off the bat, one-to-one is not like really an RNN. It's just a neural network. It's just a feed-forward neural network, what we've learned so far, because you just have one single like input. There's no sequence of inputs. It's just one input, whether that be an entire image or just whatever. It's just one input, and you feed it through the network and get an output. Keep in mind, this being like one rectangle doesn't mean it's like a vector of size. That's why I said it could be an image. It could be a big image, and the output could also be like a very long vector or whatnot, but it's just one. So think of the rectangles as the number of things in the sequence. So one-to-many, a good example would be image captioning. You feed in one thing, like the sequence is just of length one, it's just one image. You feed that in, and then you get a sequence of words, which is the caption for that image. So you could feed in this image of a dog, and you get a caption that says a cute little dog sitting in a heart drawn on a sandy beach, which is really cool. And then many-to-one, that would be like the opposite. If in someone's review, on Yelp or whatever, and then doing some sort of sentiment analysis, learning like what is contained in that review, and just giving one output, like is this positive, neutral, negative. And then many-to-many is like we talked about, machine translation, variable input, variable output. But as for the actual structure of the RNN and how it deals with sequences, like what makes it actually work, it's all in the hidden state. And so this is why it's called a recurrent neural network. As you can guess from like the word recurrent, there is recurrence. There's a recursion happening in the flow of neuron activations. So you have the input that's red on the bottom, you feed it into this neuron in the recurrent layer. And just like normal, it will feed its output to the next layer, or the output in this case, but it will also which which item in this. So let me see. This will have like a better visual here. On the left, you see kind of like the compressed, like this is what you'll see in a lot of papers and diagrams. This is like the recurrence. And then on the right, like these are equivalent. It's just showing like you could unfold what's on the left over time on the right. And it's the same thing. So if you had an input sequence of length t, then you would feed in the very first input, and there would not be any hidden state being passed back in because it's the very first thing in the sequence. And then every other token, or like every other part of the sequence after that, would be fed in the previous hidden state of the last sequence. So really quickly, Wesley asked for me to repeat the last side. So let me see, which one was that? Did you mean this one, Wesley? I assume you meant this one, but this one I was basically just saying that, yeah. So the recurrent layer in the middle you see here, it's just like a regular neuron in that it's taking in an input and giving out an activation, but it also has an extra connection. And that extra weight, it's literally a weight, just like a weight between two neurons in two different layers. But instead of being to the next layer, it's to itself, which is hence the name recurrence, or there is a recursion happening here. It's a weight to itself, and it passes on that hidden state, like that information of the previous input. That's in the next word in the sentence, or whatever, the next thing in the sequence, it has, along with the next word, some information about the previous word. So that's the whole idea. So did that make sense, Wesley? Hopefully, like the high level idea came across. But you know, yeah, awesome. And so to get a little bit more concrete about the math here, so this is the same exact thing that you saw from the last slide, but now we're just showing like the actual math. So xt is your input vector of length t. So there are t things in the sequence. Once again, one specific x, like x subscript I in this sequence of t things, doesn't necessarily have to be like one number. Like it could be an entire vector. But it's just that it's a sequence of t things. You feed that into this recurrent cell, and HT here, this is basically like the innovation, if you will, of RNNs, is that this is a weight not to the next layer, but to itself. And so so you see here the tan H of W subscript HH. That's saying the weight from the cell to itself, and then you're multiplying that by whatever the hidden output of the previous input was. Whereas W subscript XH, that's the weight from the input to the recurrent cell. So yeah, be a little more, I don't know, I guess it works. You could see it either way. Maybe it would be a little more straightforward if you put this right term to the left, because it's like, okay, the very first obvious thing is that we're taking the weight from the input to the recurrent cell and multiplying that by whatever the input is. But then the whole like memory part that remembers, has a short-term memory, is this part, which is the weight from the recurrent cell to itself times whatever the output was of the previous layer. So this might look like a lot of symbols. And to be perfectly honest, you don't need to know you don't need to like understand the math super well, But I do think like this one's a little better than like later on we're going to show LSTM math, and that stuff truly goes over my head. But hopefully this part makes sense, where it's just like the W here refers to the weights, and the HH is saying it's recurrent, it's going back to itself. And of course we have tan H like usual, a squishing function to ensure that the output is between -1 and 1. And then the output vector would just be the weight from that recurrent cell to the output neuron times the very, very final output, which is HT. So yeah, HT is based on not only XT, but also the previous HT minus 1. And then HT minus 1 is based on HT minus 2, which is based on HT minus 3, et cetera, et cetera. It goes all the way back to H1, which is based on X1. Sorry, that was like a lot of subscripts and stuff, but this visual will help for sure. So let's say you're feeding in this sentence, what time is it, question mark. So the very, very first word gets passed in, and that's it. You just pass it in, you have a weight associated with it, and then you just get an output, because it's the very first one in the sequence. Then you pass in time. But remember, so this is like the unfolding that I'm showing here. This is the very same thing as this. Like, this is the unfolding that I'm showing. Like this is what you see, but this is what's happening. So the recurrence that's going back into the second token is this information about the word what. So now the output of this neuron is not only dependent on just the word time, but also the word what. And then the same thing with you have input and time, and so on, all the way to the end of the sentence. Now, here's one thing that's important to note that you might have observed about the color distributions across this neuron. You'll notice that it's not like evenly split, right? Like you see what here takes up 50% and time takes 50%. And then here you see is 50%, but then time is 25 and what is 25. And then here it just like keeps getting less and less, like exponentially. Like what here is only like 12%, and then it sent entire activation. And that was a purposeful like design choice on part of whoever animated this. And the reason is this: the biggest drawback of RNNs is that they can only hold very, very short-term dependencies. And the reason for that is because think about it, you have this weight that's going back into the recurrent cell, and you keep on passing in the next token in the sequence. The very previous token is what matters the most. That's what's being passed in, the weight times that very previous output. And like each previous like output before that matters less and less, exponentially so. So that's what they were trying to show here with each previous word takes up, and like how little it contributes to the output of the word. So yeah, training an RNN, very similar to training a regular neural network, but there's a huge problem, and that is to do with vanishing and exploding gradients. So I'm not sure how many of you guys might have read the supplemental reading for the backpropagation lesson, but that did include some reading about vanishing and exploding gradients. I'm pretty sure I talked about this like one of the previous lessons as well, which is basically that when you have the derivative of whatever activation function like sigmoid, the derivative is very, very close to 0 at the tail ends of that graph, so that when you backpropagate through a network, you'll have like a bunch, like let's say the very, very first layer depends on the second, which depends on the layer of the third, all the way to the last layer. So you're multiplying all these partial derivatives together, and they're all like really, really small and really, really close to 0. You can get what's called a vanishing gradient, where you have like a bunch of 0.001s multiplied by each other, and it basically just goes to 0. The opposite is when the derivative is greater than 1, so that you keep multiplying and getting a greater and greater gradient until it just explodes into, and that's just not helpful for training. Now, the thing about RNN which makes them so much worse at this problem of dealing with vanishing and exploding gradients is this recurrence, this recursion that's happening. Because imagine that you have a sequence of like 100 words that you're passing through the recurrent network. You might as well, like, you can think about it as basically you're passing it in through a neural network, which is 100 layers deep. Because that's all the recurrent cell is doing, is it keeps passing it back into itself. But you could just think of that as another layer, which is what I've been trying to show with these visuals of like unraveling the RNN like over time. Um, and it's the very same thing that allows an RNN to have a variable input or output. The fact that you could just keep recurring as many times as you want, like it's up to you how many times, because however many tokens you have in the sequence, you could just keep recurring and recurring and recurring until you finish the sequence and then finally get an output. But that's the very problem that makes the vanishing and exploding gradient problem so much worse. So yeah, to solve for this problem, along with the problem that RNNs, like I said, only hold short-term dependencies, very, very short-term relations between tokens, we have the LSTM. But before I talk about the LSTM, I guess I should just take a little break here because I've been talking for a while. Are there any questions or confusion about anything that I've said so far? All right, so to solve this problem of short-term dependencies and vanishing and exploding gradients, just in general, you should just note that like a very simple vanilla RNN, vanilla RNNs just don't do that well on their own. Like it's just really hard to learn very efficiently sequentially related data from the very basic like vanilla RNN structure. So LSTMs have become very, very, very popular. And what they do is they implement this thing called a gate. And this gate, all you need to know is that it selectively remembers relevant information and forgets irrelevant information. Of course, when you start out and you're training the neural network, it's not like it just knows which relevant info to remember and which irrelevant info to forget. It's random. But by backpropagating, it slowly learns what it should remember in the future and gets better at basically remembering what it needs to. And so, like in the math, like what you'll see in papers and stuff is this term C subscript T. So this is on top of the H subscript T, which is the hidden state, the recurrence. So this bottom left diagram here, this is like actually what an LSTM memory gate does. I honestly, like, full disclosure, I still don't understand like why it's shaped like this or like what exactly it's doing. I could explain to you what it does, which is that, you know, you pass in an input at the bottom here, and just like a recurrent neural network, you have the hidden output of the previous token, and then you pass them both through sigmoid, and then you pointwise multiply them. You do, and like the legend at the bottom kind of makes it clear as well. You have like each orange box is a layer, and each yellow circle is a pointwise or element-wise operation. So you just like pass in these activations, squish them through either sigmoid or tanh, and then just like a bunch of multiplications and additions. But all you really need to know, like, you do not need to know this. You do not need to remember this whatsoever. All you need to know is that this cell, by backpropagating over this sequence of operations, it learns to forget irrelevant parts of the previous state so that it's not wasting data and it's not wasting time on focusing on those. And it remembers what is the most relevant information to remember from the past state. And it also gives it a longer term memory than like the very, very short term dependency that comes with like a vanilla straight out of the box RNN. And it also simplifies backpropagation. So that's really all you need to know. On a high level, an LSTM can increase the memory of an RNN. Like that's why, oh, I totally forgot to mention, LSTM stands for long short-term memory. So it's still short-term memory, but it's longer. And yeah, so, and it also kind of helps tackle that vanishing gradient problem. This is just some supplementary stuff, because so just as a quick heads up today, we're going to be doing some text analysis. And when you're looking at a sequence of text, it really, really helps to embed words in a way that's meaningful. And um, the most popular way to do that, there are two methods called word to vec, which is short for like word to vector, and then there's glove. Um, but then this slide is just showing another way, which is not as meaningful. It's called TF-IDF. It stands for term frequency inverse document frequency. But basically it's there are some pros and cons to it. Like word to vec and glove, they let me see if I can get this slide. Word to vec and glove, they're very, very useful because they actually the vector, literal direction in whatever high dimensional space that is associated with each word has it contains relevant information about that word. And so like a great example of this is on the left. When you convert the word king to a vector and man to a vector, they're close to each other just as queen and woman are. But not only that they're just close to each other direct, like if I subtracted queen from king, you would get this vector. And that vector is very, very similar to the subtraction between man and woman. So that if I said like, okay, take king, take all these words, convert them to vectors and do vector math. King minus man plus woman would end up to a vector that's very, very close to queen, which personally I think is like mind-boggling. Like I think that's so cool. So yeah, like this word embedding is really, really helpful because this sort of n-dimensional space that it's mapping each word to is meaningful. TF-IDF, which you'll read about in the notebook, it's kind of like a supplement. This is why it's supplementary, is because it's after we actually write the whole RNN. It doesn't have that sort of meaning to it. So it just has frequency document. Like it's not nearly as cool in my opinion. I honestly just kept this slide because it was from a previous semester, but yeah, the glove. Sorry, I guess I kind of cut out for a second there. Um, but yeah, just to bring everything back together, there are all sorts of different forms of data that we see in everyday life that would fall under this category of sequential data. Just to recap, genetic information, heartbeat data, anything that's related to time or time series data. So like the price of a stock over time, sentiment analysis, image captioning, machine translation, like Google Translate. These are all great use cases for recurrent neural networks. So yeah, and that's about it. So what we're gonna do today, I think this is a pretty cool, one of our cooler notebooks that we're gonna do. We're basically gonna get a huge corpus of texts from, sorry, not text, tweets from both Obama and Trump. And then we're going to train an LSTM network to decide between, like, given an input tweet, is it from Obama or is it from Trump? And as you'll see, you're actually going to get like really impressive results, like in the solid 90s in accuracy. So I think this is going to be really exciting. Hopefully you guys learned a lot here. I'll give like, and this is like the last call, I guess, for any questions or whatnot. But yeah, now we're officially done with this lecture. You're good to go on your like 3 to 5 minute break now and start joining your small groups and get started.